Welcome. In this lecture we talk about power, and our understanding of power actually might solve a problem that you may have already wondered about. Let's say that we've got a mountain here, and up this mountain is a trail going back and forth all the way to the top. And let's say that we have person one who strolls along, and they go from the bottom to the top, which is a height h, and let's say they do it in a time of 2 hours. And let's say that they're feeling pretty fit the next time they come up, and they run up the mountain now. And let's say that this time T2 is equal to 1 hour. We know already which time the person is going to be more tired, which time the person is going to be breathing harder. And the question we ask is, well, if the amount of work that the person does is the same both times, the amount of work that gravity does negatively is the same both times, how come the person feels so much more tired the second time when they're running up? They did the same amount of work, right? Force times the distance. So the minimum amount of work done would be mg, that would be the force you're overcoming, the force of gravity, times the height, mgh. Potential energy change is the same from the bottom to the top for both guys. So why do you feel so much more tired the second time? Because it took you half as long to do it the second time. And that's where power comes in. Power is defined as work over time. We abbreviate power with a capital P, that is not a lowercase p. And when we look for the units of power, we'll see that we've got joules over seconds, or joules per second. But remember that joules are kilograms meters squared over seconds squared. We're dividing those by seconds. And we've got a strange unit then for power. It's going to be kilograms meters squared over seconds cubed. This unit is given a special name, just like newtons, just like joules, and it's called a watt. We abbreviate it with a capital W. Named after James Watt, the guy that invented the steam engine, and the unit for power called horsepower. So power by itself is a pretty easy concept to grasp. Work divided by time. Calculate the work done divided by the time that it took, and you've got yourself your power. There are multiple relationships that come along with power because of work's relationship to the change in kinetic energy and all of that fun stuff. So let's first take a look at a simple example. We've got a crane. It's lifting a mass m, a height h. And let's say that it's lifting at a constant velocity v. And it takes some amount of time t to accomplish this fact. And so we know that the power exerted by the crane, or needed by the crane, is going to be equal to the work done divided by the time. But work, we also know, for a constant force, is just force dotted with the displacement over the time that it took. So if this guy's going up at a constant velocity, we look at the free body diagram, we've got mg going down, and we've got the tensional force going up. If it's going at a constant velocity, these two are equal and opposite. So the tension force just equals mg. So the force that the crane applies upward is just positive mg. So filling that into our equation up here, we've got mg times delta x, which in this case is h, divided by the time that it took. And that would just be the power required. The bigger the mass, the more power the crane has to use. The shorter the time that it takes, the more power the crane has to use. Because if we divide by a smaller time, we are going to be making power larger. Dividing by a smaller number in the fraction makes it bigger. The bigger h, the more we have to lift it up, the higher we have to get it, the more power has to be used. And in general, these cranes use multiple pulley systems to give them a mechanical advantage, so that actually the amount of power they use is less because the work done is less, because the force applied is less, because of the mechanical advantage. Now also, if we take a look at some of these other relationships here, power is equal to the work divided by the time. And if we also take a look at the fact that we have the equation F times delta x up here divided by t, we should remember that delta x divided by t, oh, that's something special. That's going way back in the day. Displacement over time, that's velocity. So here's another equation for power. It's force times the velocity. Specifically, it's force times with the dot product of velocity, but just force times velocity. So if we've got a constant force, which we do here, mg, and we have a constant velocity, then this right here is another way that we can calculate the power. All right? If the velocity is changing, let's say that this guy is accelerating upward, it's kind of a different ballgame. So we ask the question, well, if this crane was accelerating the mass upward, the velocity is not constant. So would it take more power or less power than lifting it up at a constant velocity? And think about this, driving in a car up a steep road. In which case does your engine use more power, higher revs, if you're going up at a constant speed, or if you're speeding up on the way up the mountain? And I think we could all agree that your engine uses higher revs, more power, more gasoline if you're accelerating up the mountain. So how do we deal with situations like that when the velocity is not constant? Go back to the original power equation. Power is equal to work divided by time. If this is the net work done on the object, then we can also say that it's the change in the kinetic energy over the time. And so if we know the initial velocity is 0 and we know what the final velocity is, then we can find the power exerted on the box. And we have to be careful with this one because we have to remember that this is the net work. And with this object, the crane lifting it up, there's not just one force acting on it doing work. There are two forces. There's mg and there's the tensional force. So gravity is kind of doing a negative power thing here, and work is doing a positive power thing here. And so when you solve this way, you get the net power. And you would have to subtract off the power of gravity, which would be negative here, to get the total power, the power that the crane exerts. All right? So to sum it up here, we've got lots of different relationships or equations to solve for power. We've got the basic one, work divided by time. We've got F dotted with V, and we've also got the change in kinetic energy divided by the time. All of those will give us the power exerted, and remember that the unit here is watts. Short and easy for this one. See you next time.